It's a pleasure to talk to you here today. There will be a few talks this afternoon having to do with E and B polarization. And that is a topic that hasn't been brought up yet. Was introduced in the context of cosmology, especially in the context of possibly detecting gravitational waves. However, it actually turns out that the most important so this was the actual technique, A and B polarization. It goes back to the work by Mark Minkowski and collaborators, as well as Saljak and Zalda. Both of them had papers back to back on what turns out to be now a very essential technique, and I will employ this technique in order to determine fingerprints, or trying to determine fingerprints of turbulence. So in a recent paper by Mark, he wrote that the most surprising result from Planck is that the E mode power in the dust polarization, so not the CMB, is that it's twice as big as the B mode power. So that is one of the important results. Secondly, it really is very different from what anybody expected until then. If you had, for example, a random polarization map, you should expect those two powers in the E and B modes to be approximately equal. Now, what are they? They are the linear polarization patterns decomposed into geometrically rotationally invariant E gradient-like modes and curl-like modes, and I will explain that. Here you see examples of two such patterns. Here are two examples of E-mode patterns. In one case, they look like an O, and in the other case, they look like a cross or a plus sign. And so these are two very different realizations of an E-mode, and what is interesting here is if you were to look at this image in a mirror, it would look the same. If you look at this image in a mirror, it would also look the same. B modes, on the other hand, are modes that have something like a swirl in the plane. So here's a swirl in the clockwise direction, inward, and here's a outward kind of swirl in the other direction. If you were to look at this image in a mirror, it would change. And likewise, this would change. So B modes are parity odd, whereas E modes are parity even. And you obtain those from just Q and U, the linear polarization, Stokes parameters, by calculating a complex polarization, Fourier transforming it in the plane, and I'm restricting here myself to the to the local approximation, unlike the original calculation in terms of global spherical harmonics. The Fourier transforms then depend on kx and ky, and you multiply this Fourier transform signal by the combination of unit vectors of the x component of the unit vector of k minus I times the y component of the unit vector of k, and then square it. Now, the polarization itself we obtain from a magnetic field, and so there can be different sources for the magnetic field. There can be, in this case, it's dust polarization. Dust polarization does align the polarization plane, and but not it does not modulate the amplitude. Whereas, for example, in synchrotron emission, the amplitude of the polarized intensity does change in scale with the magnetic field, in which case epsilon would be proportional to B perp squared, typically. Once we have calculated this in Fourier space, we again have real and imaginary parts, which we can then decompose and Fourier transform back into real space. And that still turns out to have real and imaginary parts, and these are exactly the E and B modes. And so you can play this game and verify such a picture And it is interesting in order, especially if one wants to find parts of the turbulence that are not mirror symmetric. And so one would be, first of all, asking the question, how about helical turbulence? Is it possible that helical turbulence would lead to such a pattern? So that was one of the open questions. And of course, another question is, what about patterns that we see in the sky? Could they have any such patterns? So here are the observations from the Planck work. Here's first of all the spectra of the EE polarization, which we see as a function of circular harmonics L, which we see is an excess of the B mode, and the excess typically increases with circular harmonics degree, or with wave number. These are different regions that have been analyzed in the sky. There is, in fact, some potential evidence for a positive TB correlation. And so this is shown here in red. It is away from zero. And it's interesting because a systematic TB polarization would indicate, indeed, some mirror symmetry breaking. One would actually also expect there to be some EB correlation, but the evidence for that is non-existent, and so EB seems to be zero according to those data. Here are now results from turbulent simulations. So I've used simulations of homogeneous isotropic turbulence that is fully helical to start with. So again, you do the decomposition. You find here the typical locations of E mode polarization. You find the plus structures that correspond to negative E's, and you find also some swirl-like structures in the B mode pattern. And so now we can calculate the corresponding power spectra. First of all, the power spectrum of the turbulence, the magnetic energy spectrum is the red line, so that's how it looks like. This is actually decaying turbulence, and it's magnetically dominant or dominated. So that means the magnetic energy dominates over the kinetic energy whose spectra are here. So the initial condition here was a random magnetic field. It then gradually begins to develop a self-similar decay in such a way that you have approximately a k to the -2 spectrum, as what would be expected for wave-dominated turbulence. But in this case, there's no applied magnetic field. And the peak of the power gradually moves to smaller wave numbers corresponding to larger length scales, like t to the 1/2 power. The amplitude also decreases approximately like 1/t. If you can scale them on top of each other, and then you can verify that this is indeed a self-similar spectrum. Now, regarding the E and B mode spectra, we have sort of similar behaviors in the sense that we have a sharp fall-off. Here now, instead of this k to the -2, we have a k to the -3. And in the uprising part, we do see some rise in the E mode spectrum, but not in the B mode spectrum. And we see the excess. Now, the question is, where does the excess actually come from? Here's a different representation. One typically looks at the excess of E over B. However, it is also useful and perhaps better to look at a construct that is between -1 and +1 by taking the difference between the two spectra and dividing by the sum, in which case a factor of 2 excess would lead to approximately 1/3. So we can look at such maps in two different ways. On the one hand, we can look at the map in a single slice, and on the other hand, we can look at this in the integrated case. If you look at this integrated along the line of sight. Along this line of sight, as you would do it for an observation. So we see here that that the individual slices have something close to a 1/3, corresponding to close to a factor of 2 excess. But once you integrate, you begin to have a much stronger signal in the E over B. And that's why this ratio becomes close to +1. The turbulence was fully helical. And so one was wondering, of course, is it possible that in this case we have some evidence for a parity invariant signature? And the answer is Ca, which is the parity odd part, is everywhere close to 0. So there's no evidence for any pattern, even though the turbulence is fully helical. And I'll explain that in a moment. Looking at the histograms of E and B, we see that the E polarization is strongly skewed to the left. And so that is interesting. It means that the negative patterns, which correspond to the plus structures, are much more intense or much more extreme than the O-like ones, the rings. And so we clearly have a difference then in the typical structure of turbulence. Ring-like structures are subdominant or not as strong as the plus or cross-like structures in the polarization. We see that both for single slices and for integrated. In this case, this result is for the synchrotron emission-like pattern, but it's the same or integrated polarization pattern. But the same is also true for dust polarization, where the amplitude or the local polarization intensity, intrinsic polarization, is independent of the field strength. So again, we have an excess in the E power over B. So for B, on the other hand, the difference is just between two different types of swirl, inward swirl and outward swirl. And so both are approximately equally well represented. So the reason now and here are some other examples of turbulence, in this case with ambipolar diffusion, but the important difference actually in this case, it's no longer decaying turbulence, it's actually forced turbulence. So again, we see in the in individual slices, we see here an excess, but in the integrated patterns, it actually is no longer so extreme. The reason for this suppression of the E mode over B modes is perhaps that the preference of plus or cross-like structures over O-like structures becomes reduced due to the presence of random forcing. Ambipolar diffusion, on the other hand, comparing these two pictures, does not seem to give any systematic difference, as I was hoping to begin with. So let us now come to a different realization of turbulence. And the aim now is to find out how is it possible that even though the turbulence was fully helical, it does not actually show any image or any pattern in the E-B cross-polarization, as one should expect. So here's now another situation. If you think of convection, and now we are no longer talking about galaxies, we are talking more like in the context of solar physics, you could imagine to have a convective downdraft in the presence of an overall angular velocity where the inflow is being diverted due to the Coriolis force in such a way as is shown here. This is for an inflow, which then leads to a downflow. So flow is converging, but then going down to along the downdraft. And the same is also true for an updraft. An updraft will lead to an expansion, and the flow will again be diverted according to the Coriolis force. And the patterns look the same both for up and for down flows. So clearly, both these patterns are non-mirror symmetric, and therefore we should expect, if we had helical turbulence on the solar surface, which we should actually, because the sun is rotating and stratified, we should see evidence for such patterns. So now a numerical experiment with rotating convection is shown here. We see here the antisymmetric part of the spectrum, and we clearly see here it is different from 0 for the first time. It's different from 0. If we change the angular velocity the other way around, corresponding to going from the north to the south, we have the opposite sign of the antisymmetric cross polarization, EB cross polarization. So we now see EB cross polarization can actually be different from 0. However, not for isotropic homogeneous turbulence, but for anisotropic inhomogeneous turbulence, like, for example, in solar convection. The reason for this is actually easy to understand, because in convection, we are forced to look from the top, because nobody can go inside the convection zone and look at the from downstairs upward. We have a preferential view from the top. And so this is the reason why we always will see one particular pattern. However, by comparison with the simulation of isotropic homogeneous turbulence, you are likely to see a pattern like this, which is just which you just view from the back side. Because homogeneous isotropic turbulence does not distinguish from which side you are seeing it. Whereas in convection, you are forced to look from the top. You can never look from the bottom. And so that is the reason why EB cross-polarization can actually be different from 0, but it does require violation of homogeneity. So finally, an application to the galactic neighborhood. And so now we're back to the interstellar medium. And this is work with Andrea Bracco and Simon Canellaresi and Fabio Del Sordo. The original motivation was to look at helical patterns of this type here. So you have a cylinder with two components, an axial component and a toroidal component. And that immediately means that the magnetic field will be helical. So looking at the structure from the side, we did not see any cross-polarization, and we now would also understand that. And the reason is simply that looking from this side is just equal to looking from any other side, and so there should be no preferential viewing angle or viewing position. What, however, if we position ourselves somewhere inside the cylinder? And so now we are thinking of a completely different thing. We are not thinking of this being a filament, but we are thinking of this being a large-scale magnetic field around us in the solar neighborhood, which has both an axial component along an axis and a toroidal component. And in that case, the numerical examples or experiments showed for positive polarization, the TB polarization, which here is shown in red, is negative, but it changes on large length scales, small values of L, but it changes to becoming positive for negative helicities. And so now we begin to see clearly, in this case, we have a difference between the two different signs of helicity. And of course, the way to change the helicity is by changing the sense of the toroidal component or the vertical component, one of the two. And so how is it possible? This, by the way, is the TE polarization, which in all cases is positive, even in the absence of helicity. And that is understandable, of course, because T and E are both parity even. So the reason now for this is completely the same, actually, as I was just pointing out earlier in the context of convection, because in this case, when we look at in a cylinder, we have a perspective view. So all the vectors that are parallel now correspond to a converging patterns. And so that's why we have an effect from the toroidal magnetic field, which systematically leads to an E-polarization here. And so again, we have a situation here where we can not change the viewing angle. We are always forced to having a perspective where the axial magnetic field will look like a convergent pattern. And so this is strongly analogous to the case of convection. So in conclusion then, parity even modes are the E modes, B modes are the parity odd ones. There is observationally, and Mark emphasized this as being potentially the most surprising result from Planck, there is observationally evidence for an excess of E over B, and there will be more talks about this in this afternoon. It looks like it could be connected with the skewness that is only present for the E polarization, but is not present for the B polarization. There's also evidence for the combined cross polarizations TE being positive and TB being positive, although there is no evidence for EB to be positive as one would actually expect. Of course, we still don't know whether this is really still sufficiently significant. Further work needs to be done. But if that is actually true, it would hint at the possibility that the turbulence indeed could be helical in such a way that it would be a negative magnetic field in the solar neighborhood. Thank you.
Actually, it happened that I give you extra time, but it shows my state of I miscalculated. Okay, so questions.
So you said that TE is greater than 0 because of something involving parity.
TB.
Yeah. So you said that you said it's not surprising that TE is greater than 0 because they have the same parity.
Yes. T is, of course, T temperature is parity even, and so is E.
Right, but why do they have the same sign?
I think that is not explained by this. Actually, in this case, it has to do with the fact that that we have a density structure that is strong in the middle of the structure. Yeah. So, what is your answer then?
My answer to that for the ISM is that you have a positive TE because you have density structures that cause the temperature that are aligned with the magnetic field. And so in the Planck dust polarization, you see these temperature ridges with the lines. Yeah. Awesome.
More questions? Well, in this case, a comment that this ratio of E and B also affected by the anisotropy. And we studied this.
Right. Yes. So in your case, you would expect the cross polarization, the excess to be strong if you had a strong magnetic field, if I understand correctly.
It's Mach number that we are talking about.
And really Mach number, yes.
Yeah,
yes.
and this corresponds actually to what we get at the halo.
Right.
But
So
there can be many reasons for that.
In some cases, they actually point in that direction that it is possible, but whether it is really causing, we have actually also, when the turbulence has approximately a subdominant, we also find a somewhat larger excess of E over B, but it's not as strong.
Okay.
If the TB positive correlation is caused by a large-scale helical field in the solar neighborhood, say,
yes.
Can you say what the ratio of the poloidal to toroidal field strengths would need to be to quantitatively give us what we
I think in this case it was 20%. 20%. I would need to check the details of that. I think the I need to check that.
Okay.
That was, of course, in the paper.
The
paper has appeared just earlier this month.
Okay, let's thank our speaker. Next speaker is Susan Clark. Oh, she talked. Brandon Hensley.
All right, great. Thank you. I want to talk today about two very interrelated projects done in collaboration, one with Cheng Zhang, who's a PhD student at Caltech, and one with Susan Clark, who alluded to our work earlier. And so kind of the overarching goal of this work is to try to understand quantitatively the relationship between dust polarization as observed by Planck and the H1 maps. And the reason is, as we've seen a lot earlier today, is that there's a lot of information embedded in these H1 maps that are reflected in the signal from the polarized dust emission. For instance, and I'll talk about this a bit, each of these in more detail, but the H1 can tell us how much dust there is. In purely atomic gas, the H1 is an excellent predictor for how much dust you have. The dust to gas ratio in the diffuse interstellar medium is fairly constant. The H1 is also, as we've seen, is a really good indicator of what your magnetic field orientation is, but also using the orientation at different velocity slices in the H1 can also give you some indication of how disordered your field is along your line of sight, which affects things like your dust polarization fractions. And so, we have all this information in the H1, so we'd like to relate the H1 maps to the dust polarization maps in a very quantitative way. And one of the goals of this, one of the aims would be, so can we measure the 3D magnetic field orientation? So naturally, with the dust polarization angles, you get the 2D plane of sky projected magnetic field orientation. But if we really understood dust polarization fractions in particular, then we could actually infer what that line of sight angle is. Okay, so I want to start out by talking about a little bit of a subtle effect in dust polarization and how Cheng and I are working to try to see this effect in data, because if we do see this effect, then we will be confident that we have a clear and quantitative understanding of the relationship between dust and gas, and be confident that we're actually tracing variations in the angle between our line of sight and the galactic magnetic field. So to do that, to set that up, I need to go through a little bit of dust physics. So imagine a dust grain. In this slide, the dust grain will be a football. Dust grains in general rotate in the interstellar medium. They get torqued up by radiation, by collisions with gas atoms, etc. And the grain will always rotate around its short axis. If you've ever tried to throw a football, you know that the football wants to spin over its little short axis. Throwing a nice spiral involves a lot of work and concentration. So short axis is the rotation axis. Due to paramagnetic dissipation, this short axis comes into alignment with the interstellar magnetic field. So essentially, you want to be in a frame where the unpaired electrons in the grain are not seeing a rotating field in their frame. And so that gets J oriented to B. And so you have all of your little aspherical dust grains oriented along the magnetic field, and so that gives them different cross sections perpendicular and parallel to the field, which gives rise to the polarized emission in the far infrared, the polarized absorption in the optical. Okay, so naturally this is going to depend on the angle between our line of sight and the magnetic field. So now if you imagine that our dust grains are propellers, sorry for mixing analogies on you. If our dust grains are propellers and you imagine the magnetic field is down the body of the airplane, if we're looking straight down the airplane, the rotation of the grain is going to completely wash out any polarization effects due to the propellers being aspherical. You see something that's completely symmetric, zero polarization signal. In contrast, you get maximal polarization when you're looking at a magnetic field in the plane of the sky, because you're always looking at a short axis here and then a long axis perpendicular to the field. So that orientation, no polarization. This orientation, maximal polarization. But if you think about it, this exact same mechanism will also cause a signal in the total intensity emitted by the dust grain, so total I, right? So in this case, you're looking at a short axis and a time average of two long axes, right? So you always are looking at a short axis, so you're going to get less emission per dust grain. In this case, the short axis is pointed at you, so the photons are never propagating toward you with their electric field aligned with the short axis of that grain. And so you really see two long axes of the grain, and so that enables that grain to give you more polarization. And so what this means is that there should be a subtle, not very large in magnitude, but there, anti-correlation between the total emission from dust per dust grain and the polarized emission from dust per dust grain. And that anti-correlation depends on the angle between our line of sight and the magnetic field. And we can put this a little bit more mathematically. Thinking about this here, the total intensity signal, and then divided by the total mass surface density of dust times the Planck function at the dust temperature is going to be anti-correlated. These are just some constants that depend on the optics of the dust grains, the total and polarized opacities, mass-weighted alignment function. This will be generally constant, maybe with a little bit of random variation, especially if we're looking, as we will, at sort of high-latitude local gas. And then this term, which is just exactly the same, but with the total intensity replaced by the polarized intensity. And so, in theory, this quantity is tracing exactly this angle between the galactic magnetic field and our line of sight. And we should be able to confirm this by looking at this anti-correlation between I and P. Okay, the first thing we need to actually go and hunt for this anti-correlation is a way to estimate the total amount of dust grains we have on a given line of sight. And I would argue that H1, particularly at diffuse high-latitude sight lines, is excellent for doing this. So in this previous work that I did with Daniel Lenz and Olivier Doré at JPL, we did this simple thing of correlating the hydrogen column density versus the Schlegel-Finkbeiner-Davis reddening map. And what you find is that over this range of column densities up to 410 to the 20, which corresponds to about 40% of the sky, of course at high latitudes, you see a very nice linear correlation between their estimate of the interstellar reddening and the H1 column. And the scatter in here, so keep in mind this is a linear plot, the scatter here is kind of at the level of 10 to 15%. Okay, so from here on out, I'm going to replace my dust surface densities with something that's proportional to the hydrogen column. Okay, so first thing you do is you just try it. So I have Planck maps of dust intensity and dust polarization at 353 gigahertz, 850 microns. I have my H1 map, so I can compute this. I'll just assume everything is a constant temperature and just plot I versus P. And so I'm going to be showing a number of plots that look like this, where these are 2D histograms. The colors just indicate how many sky pixels I have that fall in that particular histogram bin. And the blue lines are going to be the global median, and the black lines are going to be a running median, and the dashed green line is just going to be a linear fit. So if you look at that, well, first thing to notice is that the dynamic range is not very large in this quantity. You really only see about a factor of 2 at most change in this dust intensity per H1. So it already is indicative of how powerful H1 is at predicting what your dust emission is going to be. The second thing is, well, if you look at the running median, it looks pretty flat, but maybe a little bit of something, but that's okay. I was already very, very encouraged by this plot because there's a lot of effects that we haven't corrected here. We've really just thrown up these quantities on these axes. One thing you might worry about is, well, in these maps you might have emission that is not galactic dust, and in particular I worry about extragalactic dust emission, the cosmic infrared background. So in order to do this study, we're using the Planck maps that have been specifically designed to map the cosmic infrared background, so that contamination should be minimal in theory. So these are the GNOC maps for those in the know. Okay, so that's one thing. The second thing is that things like dust temperature variations. So if I'm thinking about intensities per hydrogen atom, my intensity per hydrogen atom is going to go up if my dust grains are hotter, and it's going to go down if my dust grains are cooler, right? So that dust temperature fluctuations is going to naturally induce a positive correlation between these two quantities. So you might have expected to see something positive here. And the same thing if you think that the dust to gas ratio is varying very much along these sight lines, that would positively correlate these quantities. So the fact that we don't see something that's a striking positive correlation suggests that there is hope for digging this out. So what we want to do is make very good dust temperature corrections. Okay, so this is just a plot of the Planck 353 gigahertz intensity versus H1. Again, these two things are remarkably well correlated. The H1 is already doing an excellent job at predicting what your total dust intensity is. But if we had a way to estimate what the temperature is, in theory, what should happen is that the scatter in this plot should go down. And we can estimate the dust temperature with the Planck data. It's multi-frequency, goes down to 350 microns. And so I've just taken a Planck dust temperature map and replaced this 19.6 Kelvin that I've assumed in every pixel with the actual Planck dust temperature in that pixel, with the expectation that a lot of the scatter would go away, and then I could go make my correlation plot and find this IP anti-correlation. But what I found is that plugging in the Planck dust temperature map is that my scatter actually got bigger. Which is not very encouraging in thinking of these dust temperatures that have been estimated from the Planck data are actually physical dust temperatures. So I actually used a number of different dust temperature maps that have been produced, and actually none of them are able to reduce the scatter that we see here, this intensity per hydrogen. And so the conclusion I would have there is that, well, evidently they're doing a good job at fitting the dust SED with these parametric formulae, but the physical interpretation of that is not what we thought it was. I really don't think that, at least in these high latitude regions, that we've really grabbed onto true dust temperatures. And so without being able to do a great dust temperature correction, there's only so much we can do to find our correlation in magnetic fields. One thing we've tried is just binning the data into different dust temperatures, with the idea that being that if it has the same dust temperature, then it has a similar looking SED, so it might have the same true dust temperature. And if you look at, particularly in the top left plot, you see exactly the sort of pattern that you would expect from this IP anti-correlation, where you have an excess of points above the median at low polarized intensity per hydrogen, and a deficit below the median at high polarized intensity per hydrogen, with a slope of approximately -1. So that would be a great signal if it persisted across the temperature bands, but it is not. And another concerning thing is that, again, in each of these plots, I'm assuming a constant temperature, but the y-intercept is actually going down as the temperature goes up, which is the opposite of what you would expect if those were true temperatures. So unfortunately, we're kind of hamstrung a bit there, and would be grateful if anybody had additional ideas of things to try to make our correlations a bit tighter. But I think the principle is still good, that this is a way that we can test to break this degeneracy in polarization fraction. Is the polarized intensity low because the magnetic field is very disordered, or is it low because of geometry effects? And by looking at this intensity versus polarization anti-correlation, which would, in principle, give us the third angle for the magnetic field. And then the other thing, particularly for the Cmv folks in the audience, is that now I have a whole lot of skepticism for the degree to which we can trust the Planck models in any corresponding to detailed dust physics. And so maybe we need to be rethinking about the way we're parameterizing, or even think about ways we can incorporate, say, the H1 data directly into our model fitting. And then I've kind of left open this issue of line of sight depolarization, this magnetic field tangling, and that kind of brings me into the second part of my talk, which I will dive through in just a few minutes. So, 2 minutes? Excellent. And as Susan showed earlier in her slides, the hydrogen orientation, so these linear filaments do a very excellent job at predicting, at tracing the magnetic field, the dust polarization angles that we see with Planck. However, you can also think about doing that channel by channel. So this is Susan's paper from last year, where these are plots now of H1 velocity is on the radial axis, and then the actual orientation angle plotted as an angle. And the idea being is that if all of your structures that you see along a given line of sight fall at the same orientation, regardless of their velocity, that means that along that line of sight, the magnetic field is probably pretty coherent. And so you don't have this effect where magnetic fields at different angles are canceling each other down, and you end up with a smaller polarization at the end. So you can contrast the top image there, which is where things are very coherent, at fixed, all of your gas is at fixed theta, essentially. Whereas down here, you see that you have a lot of gas at orientation 1 and a lot of gas at orientation 2. And so what you might predict is that the top image corresponds to a region where you see high dust polarization fraction modulo the line of sight angle, and the bottom image where you would see lower dust polarization fraction. And so we're able to do that using the high 4pi data, able to map the H1 orientation over the full sky. So this is what you would predict just from the H1 data itself, and this is the Planck 353 gigahertz orientation map, and you can see just by eye, there's rather excellent correspondence between those two. But additionally, this is now the polarization fraction versus this parameter that characterizes how coherent the H1 is in orientation as a function of velocity. And this is what we say should be predictive of what the dust polarization fraction should be. And indeed, you see a very nice positive correlation between those two quantities. You might say, oh, well, there's a lot of scatter here too. Well, of course, this H1 coherence parameter doesn't know anything about that line of sight angle. So, at any fixed coherence, you could still end up with no polarization or maximal polarization, just depending on the viewing geometry. So the fact that we see this really excellent correlation tells us that we really are capturing something about the line of sight depolarization, and that maybe we could use that with the total polarization fraction maps to estimate this line of sight angle, because we now have a way to quantify how much of that depolarization is coming from these line of sight effects. And so last slide. So in summary is that the H1 is giving us information about the amount of dust, the orientation of the magnetic field, and the degree of depolarization along the line of sight, these line of sight effects. And so there's a few things that we can think about doing with that. One is that we can use the H1 data, kind of forward modeling approach, the H1 data, the full velocities, et cetera, to make simulated maps of dust polarization. And that would give us things like simulated foreground maps that have non-trivial spatial statistics on small scales, which is useful for Cmv lensing. It can also let us test things like how big of decorrelation between frequencies do we expect due to these 3D line of sight effects. And then finally, we can also think about applications for learning about the interstellar medium and magnetic fields. Things like, well, the H1 orientation argument is only tracing these, cold filaments. There's a lot of H1 gas that doesn't get, in one of these. Is that gas oriented in the same way as those filaments, or is it completely random? And we can test that by making maps that one assumes the random orientation, one assumes the coherent orientation, and seeing which one is more predictive of the dust polarization fractions that we see. So all of this is work still ongoing, so stay tuned and eager for your thoughts and feedback. So thank you very much.
So you showed that the Planck dust temperatures don't seem to be physical temperatures.
Mm-hmm.
Based on what you determined.
Can you use your microphone, please?
Yeah, well, I pushed the button. Okay, maybe I got to talk into it better. So you showed that the temperatures that Planck produces don't seem to give the behavior you expect if they were real physical temperatures.
Right.
What is the total variation in temperature that you get? Is it 1 degree or 5 degrees?
Oh, right. So the full range of the Planck temperature map that I showed was something like 18 to 30 something. In general, I think the variations are probably mostly within 20–30%.
Of the ones you use in your analysis, they're all within 20 or 30%.
So we without an a priori way to estimate. So we use just all of the sky that falls within our H1 cut. So in theory, we'd be using everything.
I see. Okay.
Yeah.
Thanks.
Oh, Laura?
Considered binning your data by the degree of dispersion in the line of sight component of the magnetic field from the polarization? Because you would imagine that if the field is pointing towards you, then you would, in the projection to the polarization observations, you would see much larger dispersion in the polarization angle, right?
So we haven't looked at the S parameter, the polarization angle dispersion parameter, which would definitely be something interesting to look at. We have looked at the TH1 parameter that I've just shown, which should help us select regions that don't have a lot of the line of sight depolarization. And so far that hasn't helped a lot, which is also interesting.
More quick question about the Planck dust temperatures. Have you considered looking at any of the regions that Herschel observed to see if the higher frequency data there helps determine the temperature more accurately?
That's a good idea. So no, we haven't done that. I feel like there's probably a big discussion we could have about this. Part of it is that there's no map that one has CIB filtered out, because if you look at, like, for instance, the commander maps, and I tried to do this, the CIB, because I didn't try to separate it out, would just destroy it. Their temperature maps look like CIB at high latitudes. So this is really kind of the only temperature map that is that is valid at the H1 columns we're talking about. And if you look at the maps also, there's a really strong T-beta correlation in those maps, which make me even more convinced that those are not physical temperatures.
Let's thank our speaker. The next speaker is Alexei
Oh, okay, so I will reuse the very nice introduction made by Axel to the problem of general Planck results and how they can connect to turbulent simulations that we do. And so in this work, I'm asking a very simple question. So can we come up with some very simple numerical model in a minimalist sense that it includes as little physics or astrophysics as possible to reproduce Planck results? So that's the philosophy behind this work. And so apparently it is possible, and the model appears to be very simple, actually. So when we were modeling star formation, normally it's a multi-scale process, and so in order to get to protostellar cores and collapsing young stellar objects, we need to model the inner structure of molecular clouds. But when it comes to using MHD for this modeling, we need to know what kind of magnetic field threats this cloud. And in order to do that correctly and numerically, we need to go to larger scales to reproduce the field geometry in a natural way. And so at some point, we came up with this formulation of MHD models with multi-phase ISM in boxes which are comparable in size to the scale height of the disk. Okay, and so this turbulence is quite different from what we previously have done and many other people have done in the isothermal approximation, because it includes different phases, right? It includes warm phase, WNM, CNM, and all these thermally unstable regimes in between. And so, and if you, the physics of turbulence, though, is different. There were nice questions actually asked yesterday by Jerry, whether this turbulence has some boundaries and is different in different phases. So this is a classical case of inhomogeneous system because we have two phases, at least for that reason. And so, of course, turbulence has different properties. This has been shown a long time ago. So in the cold neutral medium, it's mostly supersonic and probably superalphinic as well. While in the warm gas of lower density, it would be transalphinic or subalphinic, and slightly transonic perhaps. And so this means that on even smaller scales, gravity will play an important role. And we have actually an inhomogeneous system with different types of alignment. So here in the low density stuff, the alignment is in between velocity and, magnetic field, like Alfvén effect. Alignment is different in the cold phase, and it's like Zeldovich alignment between the gravitational acceleration and velocity at high densities where gas becomes self-gravitating. So with this in mind, let me just walk you through the story. So our simplest model is this multi-phase turbulence. We solve ideal, quotation marks, equations with some additions on the right-hand side. So here we have forcing at large scales to mimic the injection scale of 100 parsecs in the box. And we also have cooling and heating functions responsible for this multi-phase structure. Okay, otherwise there is nothing special in this very simple toy model, I would say. Okay, so we parameterize the model in order to match the conditions at the solar circle, which would be corresponding to local molecular clouds, which have low star formation rates. And so we tune thermodynamics to basically reproduce this thermal equilibrium curve quantified by Valfire et al. 2003. We want to check whether we are able to reproduce the mass-weighted pressure, thermal pressure distribution in the local ISM. We would like to match the, the forcing intensity so that we get the right Larson's law here. And we also would like to reproduce the magnetic field strength, which comes from Dick's work. We cannot go further in density at this low resolution that we have. So, and we do not include self-gravity, which is not important for Planck's resolution. So we are mostly interested in this part of the business. Okay, and so now the model was quite successful in reproducing all these details of the local ISM, and so we are pretty sure that everything looks right. We get very low star formation rates, which we can estimate even without including self-gravity. This is trivial. So now we would like to see whether this simple model can reproduce Planck's result. And so these are different, so this would be the slopes of the power spectra for E and B modes. I will not introduce them because Axel did this nicely for me. And so the slopes are around minus 2.4. And so this old data release assumed that the slopes are probably similar, while there is a little difference here. Okay, but the new third release, I think, shows that there is tentatively little difference in slopes on the order of 0.1 between E and B modes. Okay, so now you can. So this shows the fraction of the sky in different masks. So the smallest fraction is this yellow part, and then other cases combine all the different colors progressively. Okay, so here we are looking at Planck results with respect to B to E ratio. It's inverse E to B, right? And so it looks like what Planck shows is that the ratio is on the order of 0.54, roughly. And that translates into 1.92 if you want E to B, okay? So then polarization fraction PDF, probability density function, looks like that. And this is the fiducial model. And these are two more specific models that showed how confident we are in this distribution, okay? So we will try to see whether these results can be recovered in a very simple two-in model of the ISM turbulence. And then the other question we ask, so if we can recover that, why do we get this E to B ratios? Why the spectra? So why the model is working? So that is a question about physics. And so I have several models to pursue this, to improve our understanding of this. So there are two multi-phase models which differ. So it's 200 parsec box, 5 particles per cc, mean density in the box, which is roughly what we would expect in the Perseus spiral arm. It's a little higher than it would be needed for Planck and CMB business, but this is what we got for in our old models designed for star formation studies, okay? And so then the mean field values are about 10 and 3 microgauss. We are using solenoidal forcing in both cases, and mean regimes in terms of sonic Mach number and Alfvénic Mach numbers are like this. So 5 and 0.5. In this model, we have 5.4 and 0.7 for the Alfvén Mach number. Okay. We also have two isothermal models to see whether the idea of mode decomposition would work to explain the asymmetry in E and B power. And so here we use isothermal models with high resolution, 1024. All these numbers are dimensionless, of course. And so these two models, B1 and B2, differ in terms of the strength of the mean field, right? Also solenoidal forcing. So here we get Mach numbers about 10, and we get Alfvénic Mach numbers 0.6 and 1, okay? And then we have, because people were discussing that maybe the reason for E to B is in the forcing. So we wanted to have some diversity of forcing. So this model C star comes from, data come from Paolo Padoan. He kindly shared the data. So the resolution is higher. The box is very similar. Mean density is the same. RMS velocity, which normalizes the forcing strength, is the same if you recalculate it to this scale. And then what we get, the mean field is in between, okay? And then this is forced by supernova feedback. And, but Mach numbers that we get are oscillating due to supernova activity. And so the range of sonic Mach numbers is roughly the same as here globally. And the Alfvénic Mach numbers are substantially higher, okay? So now let's see what we get. So this is our one multi-phase case, and what you see is just, oops, okay, just the column density movie. So here we compare the column densities that we have in that model, and we overplot them onto the H1 for pi survey map to show that these areas are outside the range that we have in the simulation. All this other, and these areas along the Milky Way plane are also outside. But we still cover large high latitude areas here and there, for example. Okay, so then we put in a trivial dust emission model. So we just assume optically thin dust radiation, constant dust to gas ratio, grain alignment, does not depend on density, and we use flat sky approximation, as simple as that. Okay, so then we can compute I, Q, and U, and we can generate synthetic polarization maps. So the texture here shows the plane of sky magnetic field direction, and this black pseudo vectors show the polarization direction. And so they are perpendicular, and you see this typical structure. The mean field goes along the axis in these models. And so that's, you basically see what you expect, right? So if you look along the magnetic field, now it's like that, the structure gets more complicated, but overall it's the same kind of alignment that you expect, okay? So then we can decompose the modes, and we can look at this power spectra. So here I show B mode power spectra, and lower panel shows the E to B ratio is a function of wave number. Okay, so we see that the power spectra, we have to mask some of the voxels because we don't have enough resolution in this model to resolve the dense gas which cools very, very quickly. And so we mask, but it's a tiny percentage of voxels that we have to mask, okay? Okay. If we mask a little bit more, so we exclude all the densities above 70 particles per cc, we get close to the Planck result, okay? And so if we mask a little bit more, it's 1.4% roughly, we get pretty nice correspondence to what Planck sees in both spectral slopes and E to B ratio. Okay, so now what we do when we mask, we basically strip off, this is the PDF of the plane of sky magnetic field. So we strip off long tails in this PDF, and we recover Planck results when we cut them off like this, so that the remaining distribution is exponential. Okay. So these guys come from intermittency, which most likely has numerical origin, and it would depend on resolution. So if you throw away all this garbage, you get Planck, okay? So this is model B2, same kind of masking, weaker mean magnetic field. You get kind of close to 1.9, but not really there, but still the spectral slopes are similar to what Planck sees again. And so the truth for the local conditions is somewhere in between models A1 and model A2. Okay, now model A1 reproduces the PDF of polarization fraction quite nicely. I think the shape is very similar to this red fiducial case. And so let's now look at either thermal models. So this is again a movie which shows evolution of column density. Amazingly, so here we have to mask a little bit, just 0.2%, to get a very confident result for E to B, about 1.9 across a wide range of scales. And actually, the spectral slopes look very similar. So this is either thermal model. Completely different physics, right? The regimes were listed in that table. Yes, please.
Which Mach number, which alpha Mach number was
This is 0.6, I believe, alpha in, yes. And so that fits nicely the theories that developed by Kandel, Alex, and Pogosyan. Now let's look at model B2. Now the alpha Mach number will be 1. And wow, still we have the same E to B ratio, right? That's nice. And the slope is a little bit more shallow, but still pretty close to what is expected. Okay, now this is a model with supernova forcing. You see the case looks different. but also the Alphian Mach numbers are much higher than in all other models. So this is again multi-phase model. The slopes of the spectra are very similar, again 2.5, pretty close to 2.4 as observed, but the E to B ratio are off by quite a little bit, right? So I was looking at details of how this thing evolves. Maybe I can show it once again. And it's consistently below. There is nothing, this activity comes from the forcing, okay? So this is my summary, and I think I will stop.
Can you use your microphone, please?
Okay, so does the result imply that interstellar turbulence has most energy in solenoidal mode?
Oh, once again, it has what?
So so the differences by different driving, by different forcing mechanism, and does it imply that interstellar turbulence has its most energy in the solenoidal component compared to the compressive?
I see. I think it could be the problem with multi-phase supernova-driven simulation could be just in the way how numerics treats supernova driving, because the Alpine Mach number is off from what we know the observations give us, right? It oscillates between 1 and 8, so it could be that under-resolved supernova explosions on this grid would dissipate too much magnetic energy and would never give a chance for magnetic energy to get amplified. So that's my interpretation of this negative result in the supernova-driven case.
But if you already have the alpha Mach number larger than a unity, do you expect that this should act to change?
Yeah, that's of course. But the problem is, why is the Alpine Mach number so high?
Okay.
Because it's the only difference is driving. The mean field, the magnetization is roughly the same. The sonic Mach number is roughly the same. The intensity of forcing is the same, but the result is different, right?
Yeah, it could be that we're putting more in Blixley.
So it's a really nice controlled experiment, and I'm wondering what your opinion is on, is it the alpha Mach number that's primarily controlling the amplitude of the E to B mode ratio, or do you think it also has to do with the phases? Because I can't quite remember what the alpha Mach number for the multi-phase gas was.
For the multi-phase, for one model, it's about 0.6, I think, okay, so 0.5, and the other one is 0.7 something. So we are working on that. It's a non-trivial question. I think it's a complicated system, and actually, I think different modes would be excited by different forcing, and different modes would produce different E to B ratios. And so we are trying to figure out how this thing is working, and there will be a paper pretty soon summarizing this work.
I think it is interesting to see how this ratio of compressible and incompressible turbulence is changing with K. I expect that eventually you will be increasing the solenoidal component if you have a significant inertial range.
I think, yeah, maybe, yeah. We certainly need to go to higher resolution, so that's the perspective. So we will run much larger, 10 times cubed larger simulations pretty soon. So the code is working good and scaling nicely. So
no more questions. In this case, let's thank the speaker. The next speaker is David Collins.
This is ship sterns. People surf on this. It's like 30 feet of ultraviolet water. Here we go. How's my technology working? Sweet. Okay, so I'm going to talk about ostensibly some of the same stuff that that Axel and Alexei's talked about. I'm going to talk about interpreting Cmv foregrounds, and I'm going to show up 2 slides on Type 1a supernova because they're really cool. Also, because I have a grad student who needs a job, so I want to advertise his stuff. So I'm going to talk about Cmv foregrounds. I'm going to show you, first I'm going to start with some simulations that didn't work. But now that I've heard Alexei talk, I know why they didn't work. And then I'm going to talk about real space interpretations of E and B, because I don't really have a very good intuition for E and B. But one of my collaborators, Kevin Huffenberger, has developed this real space interpretation that works very nicely. And then I'll talk about modeling this with filaments. And then I'll talk very briefly about Type 1a supernova. I'll give you a very unsatisfying introduction, and then I'll show you some cool movies. Okay, so E and B are the rotationally invariant versions of Q and U. The pictures that you see a lot are this radial thing and this circular thing and this fanny thing and this other fanny thing. But the results have come up several times already. So we have the ratio of B to E is about 1/2, 0.52. The slope goes like multipole to the minus 2.4 something. And the T to E ratio goes like 0.3. And this is a pretty robust result across the sky, so we want to see if we can make pictures, so get some interpretation of this. So this is a simulation that almost works. So this is a 512 cubed box with a sonic Mach number of 9 and an Alfvén Mach number of 9. This is the same data that I've used with Blakesley to do star formation before we turn gravity on. And with this, we find slopes in E and B that are maybe a little steep, but not too bad. But the ratio of E to B is unity. So, well, let's try a stronger field. So if we have a sonic Mach number of 0.6 and an Alfvén Mach number of 0.3, why did I pick those? Because this is fast to run. We get the ratio right, but the slope is far too steep. So this ratio is a little high, but it's also the cheapest simulation that I could pull off. So we did a suite of simulations where we varied the sonic and Alfvén Mach number. And so this is a diagram that shows the Alfvén Mach number here and the velocity, the sonic Mach number here. So this is a sonic Mach number of 1 and an Alfvén Mach number of 1. And we were targeting supersonic and subalfvénic simulations. So I have each point is a snapshot from the simulation. I didn't do any fancy averaging because I was lazy. So we have a transonic, slightly subalfvénic, and then several other supersonic simulations, a subsonic one, and this simulation that ostensibly was going to be super alfvénic and subsonic, but decided it was going to be transonic. This is not a relaxed simulation. This is what it happened to be doing at the time that I analyzed it. So if we look at what the ratio of B to E, so this is B to E of 1. This is what we want to see. B to E is 1/2 versus the slope. We find that, so the supersonic, super alfvénic simulations that I wrote other papers with are way up here, where the slope is right, or maybe a little high, but the ratio isn't quite right. Oh, I take that back. That's not the same simulation because that had a lower. Anyway, the closest that we get is this suite of simulations here that are not particularly relaxed. They're not in a kind of statistical steady state, but our ratio somewhat depends on, the ratio of B to E somewhat depends on the sonic Mach number, where more supersonic simulations are giving us a B to E of 1, but we're not getting the slope right at all. So why is that? it has to be the resolution, because I'm running simulations that are very similar to the simulations that Alexei was running, but these have much more poor resolution. These are all 256 cube boxes. So I think that the resolution clearly can determine the slope because most of the box is in the dissipation range. So if we're going to be doing anything like this, I'd be curious to see if Alexei has any crappy simulations that I could compare against to see if he sims. Of course not. It's possible, yeah. That's also true. I haven't done any. Alexei had cut out some of the rare peaks, and I haven't done any of that. But I don't think. Which direction would that make things go in? That's going to make all the slopes shallower. So I think I'm not going to run into that problem because it's all too coarse, I think. I'm pretty sure that you have to have a lot of resolution to make this work. So in the meantime, while I was waiting for simulations to run, we started thinking about other ways that we can interpret this data so that I don't have to run 1,000 cube boxes because, again, I'm lazy. So we'll go look at what people smarter than me did. So these fantastic maps show that that filaments are oriented along magnetic field lines, which you've heard at least once today. So what does this look like? What does a filament look like? What does E and B look like on a filament? So, okay, my complex polarization looks like this, Q plus IU. So the bits that I'm going to need, we're going to rewrite this as the polarization fraction, which is just the norm of this divided by the column density times the angle. So we've got the polarization fraction, some orientation, and then the mean density or the mean temperature and some shape function. So we're going to take our fake filament and parameterize it by some shape function, and we'll have some polarization fraction that nominally goes like sine squared of the angle to the line of sight. So then E and B are the Fourier transforms of E and B are e to the 2I theta L, where this L here is multimode or multipole, and then this is the complex polarization. So this is the same thing that Axel and Alexei have shown. So what does this look like? So what Adichie Rodi and Kevin Huffenberger came up with was they sorted out what the Green's function for E and B looks like for a delta function in Q. So if this little bit here is Q, a bit of E mode looks like a flower where you've got a positive lobe here and a negative lobe transverse, and B is that rotated 45 degrees. So if I have a little bit of Q polarization in this positive Q is this direction. This is real space. This is what a real space E mode looks like from a delta function in Q. Does that make sense? Me too. So if I've got a filament that looks like this, where my polarization is perpendicular to my filament, then I take my little E mode Green's function, and I can just paint that along my filament, and I get positive E along the filament and a slight negative E transverse to the filament. If I'm looking at the B mode signature, the B mode has odd parity. So as I paint this up my filament, most of it cancels except towards the ends of the filament, where I get E and B in the corners of my filament. So if I have a filamentary structure and my field is lined up along the filament, it's going to give me E and not very much B. Does that make sense? So I have a lot more intuition for this. I don't know if this is obvious to other people, but it took me a minute to get my head around it. So if you want, I can go back and say that again. Okay, so the sky looks like a bunch of filaments. So if we parameterize a filament as this kind of somewhat elliptical object that has a long axis L and a transverse axis, and its overall prolate spheroid, and there's a magnetic field that's at some angle to it. Well, so nature's got to be roughly homogeneous, so we'll average this angle azimuthally. We want it to be azimuthally symmetric, and we'll have some distribution of angle with some variance parameterized by an angle, which I'll talk about in a second. This is the same thing that Brandon was talking about before, if we look at the angle, at what the polarization looks like as you orient a filament towards you, the polarized emission, the emission will go with a filament will be strongest as it's aligned towards you because you see most column density that way, but you won't see much polarization. Whereas if the filament is transverse to the line of sight, you'll see a lot of polarization, but less total intensity. And since the polarized emission goes like the product of the temperature and the polarization fraction, you get this, this double humped kind of profile that peaks around 45 degrees. And depending on the misalignment axis, you'll get you'll increase the alignment along the line of sight when the filament is along the line of sight, because you'll see some polarization because it's azimuthally symmetric. So I can parameterize my, here it is. So I can parameterize my sky as an ensemble of filaments of various length. So the things that are important are the long axis and the short axis of the filament, the line of sight, or this plane of the sky polarization psi, and the line of sight orientation of the filament and the magnetic field. So we're going to marginalize over everything other than the axis ratio between these two things and the dispersion in the angle between the filament and the magnetic field. So we can build up what our whole power spectrum looks like by doing an ensemble average of a bunch of these filaments, and that looks like this. So my E signature is going to be an integral over the angle and an integral over alpha, where alpha is my full set of parameters, times the number of filaments with each parameter set times E squared. And B squared and T to E is going to be T times E star. So if I want the sky to look scale-free, which I do because that's A, easier, and B, it looks like turbulence, and C, I can then do something with it, then I could take this, this ensemble average and rewrite this as a scale-free function. So this is F. F is going to be E squared, and we're just going to parameterize this by alpha times the multipole. And we can rewrite this, this scaling relation if we assume that the number of filaments with some alpha scales like alpha to the p, then my multipole scaling goes like L to the p plus q plus 1, and that over r. So this is just calculus for scale-free things. So what can I do with that? What's alpha? Alpha is all this stuff. Well, if I just say that my scaling parameter is the length, then the column density, or the E mode scaling will go like the column density of the solid angle. So P here, Q here will go like alpha to the length to the 6th. And I know what CL needs to be. CL has to scale like L to the minus 2.4. That's what the sky tells us. So this tells me that the number of filaments has to scale like L to the minus 4. This is something that we need to go check. There are many knobs on this. As a scale-free process, there aren't very many knobs because this is fixed by the sky and this is fixed by geometry. So this is a thing that we can go check, but it's a robust prediction about the size of filaments if we can, in fact, decompose the sky into a bunch of filaments, which we could talk about if that's, I like it as an idea. So what is the behavior of the spectrum? How does that shift with the aspect ratio of the filaments? So that's the primary knobs that we're going to look at are the aspect ratio of the filaments and the misalignment of the field and the filament. And so that's the dispersion in the misalignment between the field and the filament. So E to B is as you change the aspect ratio. As I change the aspect ratio of this, I'm going to have per unit temperature more endpoints per length. So there will be more B per unit E. So as I shorten the filament, I will get a larger B to E ratio. As I change the misalignment, as I'm misaligning, so if my filament is up and my magnetic field we're averaging azimuthally, then I'm going to have less polarization along the filament, so my E will go down, but my B won't change much. because the B just comes from the corners. How does this depend on T to E as well? So again, since my field is mostly along the line of sight and my Green's function is a flower that travels along the polarization, my polarized filament for the most part gives me E. As I change the mean, the net alignment, as I change the net aspect ratio, I'm going to have fatter filaments. So we'll have less T to E overall because we'll have more B. 2 minutes. Time flies. And similarly, the T to E on less alignment. So we have these knobs where we can control what the spectrum looks like. So I know what the slope ought to be because I have the sky. And we can see that we have a degeneracy between the aspect ratio and the misalignment axis, but we can get the slopes that we want quite nicely. So now we just need to go look at what the sky is telling us, and is this a consistent picture? It's nice to build intuition. Like, I feel like after having done this, I have a little bit better intuition for what E and B are. Whether or not it's an accurate picture of the sky, I can fix that because there's plenty of knobs on this model. So, so if we have our RMS field is like about 35 degrees and our axial ratio is about 0.2, then we can reproduce the B to E ratio quite nicely, and we can also reproduce the T to E ratio quite nicely. Now we can tweak these a little bit because we know that the polarization fraction isn't going to be as constant as I would like. So there's some degeneracy here that we can play with. Additionally, and I think this was brought up in a question before, if we look at the distribution, so we're averaging my field azimuthally. If we look at the distribution of the line of sight field angle, so these are probability curves, we find that as we decrease the line of sight field of the filament, the projected, this is, oh, that got cut off. This is the projected field angle in the plane of the sky gets much wider even for fixed projections because we have this distribution of stuff. Okay, that says I have 3 minutes left up on the thing, so I'm going to spend 2 minutes on supernova. Okay, supernova, type 1A supernova. Oh, it does. Sorry. Oh, he's supposed to stop me 5 minutes ago. Okay, I'm just going to leave this up because it's cool. Turns out blowing stuff up is really fun, and if you blow stuff up with magnetic fields, that's also fun. So Boyan-Hristov, if you're interested in supernova, and like not supernova driving like magic paddles, but supernova actually blowing up, Hristov has done some really nice work. All right, I'll stop there. Well, so when I have an ISM model, I put in supernova, but sometimes you want to start with an actual star. So this picture here is a chunk of a carbon-oxygen white dwarf, and we start off with on this is carbon. This is nickel fraction, so this is all burnt to nickel, and this is carbon-oxygen that hasn't been burnt yet. This is distance, so this is a chunk of a star that is kind of radially outwards. So the center of the star is down here, and this is where we start burning. And the burning front propagates upwards towards the top of the star. And it becomes Rayleigh-Taylor unstable because that's what happens. So you get these fingers that are Rayleigh-Taylor fingers that are driven by the burning and because you're heating it from the bottom. So this is a pretty classical thing to do for modeling spectra for type 1A supernova. But if you impose magnetic fields, it flattens out the front, and it slows it down until sometimes it doesn't. This one's wound up going much faster, which is interesting. I'll talk about that later, though. So this is, much smaller than anything. So this is, the units are, this is in kilometers, so this is 120 kilometers. Sorry. Other questions?
Why there is a transition between 10 to the power of 10 and 11? There's kind of transition there in the, you see?
Right here?
Yes.
So if
What's that?
if you do stability analysis on the Rayleigh-Taylor instability, so this is out of Chandrasekhar's Magneto whatnot book, that one. Thank you. So the hydromagnetic and hydrodynamic stability text, he goes through Rayleigh-Taylor with various field geometries. So this is just where the field is suppressed. So the Rayleigh-Taylor will grow in that direction. If I have a field along this direction, it doesn't suppress the growth at all. But it does, interestingly, suppress the burning. So I keep this very corrugated magnetic field front, which winds up accelerating. So the very strong one goes very fast. But for this one, the field is in the plane of the supernova. It suppresses Rayleigh-Taylor. So just because of the magnetic tension. So yeah.
Yeah, I just have a quick question about this filament model. So everything you described basically was in the context of what I might call like the one filament term.
That's right.
Are you also trying to model the two filament term that should arise from correlations between two filaments?
Yeah, we'll do that next.
Relevant on large scale.
Yeah, I think that's right. So presently, that's exactly right. This is just a one filament model. The two filament model will show up for larger correlations. I think the two filament model may also show up with a line of sight correlation, because we know that we probably need to be depolarizing along the line of sight. But this is kind of where we've gotten so far. But that's coming next, I think.
Well, my comment would be, there is a possibility, yes. Consider that you have uniform magnetic field and you distribute densities. And polarization, indeed.
Could you please use your handheld for the people on the internet?
My comment is the following. You may have indeed uniform magnetic field and put the density filament. And as the polarization intensity will be the convolution of these two things, you will have the effect that you are discussing. There is another different model, completely different. You can consider isotropic distribution of density and make magnetic field anisotropic. And this is correspond to low alpha Mach number, alpha and Mach number turbulence. So this is an interesting question, and I hope we will resolve it very fast. I hope I turn to medicine and do the corresponding analysis. We'll see what is happening, whether we do have these filaments that I learned from Susan today, or we have, as I was implying for a while, anisotropic turbulence. The only thing I know is that for we have also this ratio, E and B ratio, for synchrotron. And the synchrotron, these visual filaments are much less prominent, but we still see the same ratio. So my thinking is that the jury is still out.
Yeah, I'm certainly not saying that this is the whole story, but it helps me understand.
Okay, let's thank the speaker. And now, very important announcement. We'll hear from Carl Heiles. No? Wonderful.
Yeah, I would actually. Oh, yeah. Thanks. So time to look at some real data. This is the last talk, so I'll try to make it short and sweet. I wanted to talk about Zeeman measurements of the 21 centimeter line measured in emission. We're all worried, most of the measurements that are quoted are done in absorption, but in fact, we have a lot more measurements done in emission over the years. Why do we bother to do this? Because the ISM and the gas and the magnetic field are interrelated. We need to know what the field is doing. So here's a view of the North Polar Spur superbubble, which goes like that. And you can see that the expanding shell has swept up the field lines, and we have a distinct relationship between field and gas motions. But which controls which? That depends on the ratio of the gas pressure to the magnetic pressure. And we can measure the magnetic pressure by looking at absorption, and we can do it in emission. And we get different answers. So here's a classical absorption line study that everybody always, well, that I wish that everybody would always quote, done with Tom Troland. We call it the Millennium Line Survey, the Millennium Survey, done at the turn of the millennium. And the basic result, there's a well-defined median magnetic field of 6 microgauss. That's the total field. That is, if the total field is 6 microgauss, typically you're going to measure half of that, because the PDF of the ratio between total field and line of sight field is flat from 0 to 1. So the median value is a half, and the mean value is a half. So such a magnetic field strength gives you a magnetic pressure that's about 3 times the thermal pressure. Now in emission, Tom Troland and I started in the 70s to measure a lot of positions using this 85-foot telescope. Tom did his thesis on it. Then he left and started working on denser things with Dick Crutcher. And I kept using the same old telescope until I couldn't use it anymore. Got as much out of it as I possibly could. During that time, we looked at 429 positions, spread over 5 papers. I want to concentrate on this paper, which really talks about the magnetic field strength in swept up shells. Here is the distribution of all those measurements. We tried to look at shell walls, where you expect the field to be high, because we wanted some detections. Some shell walls up here. This is the big North Polar Spur super bubble, which winds around over here. And wrote a paper about this, and found 73 positions located in morphologically distinct H1 shells, and the shells look filamentary. The magnetic field in those shells, 6.4 microgauss, but this is the line of sight component, not the total component. I quoted the total component for absorption, and it was 6 microgauss. The total component for emission is twice this value, which is 13 microgauss. That brings the magnetic pressure up to 16 times the thermal pressure, which is not unreasonable because you got this dynamic pressure associated with the expanding shell. The nice thing about looking at emission is you can choose positions based on any consideration you want, like interesting structure, as opposed to absorption, where the positions you choose have to have a background continuum source. So you can't do any mapping. But we can do mapping here, and in particular, we can compare the magnetic field as measured in 21 centimeter line, that is the Zeeman experiment, the Zeeman effect. We can compare that with the Faraday rotation measures, which have recently, in the past few years, blossomed to the point where we have a total of 37,500 measurements over this part of the sky. This part of the sky is the southern part of the sky, and hard to get data there from the north. All these data from the VLA. So what I did was I took all those measurements and emission we got, and I put them down on here and plotted point by point to see how the correlation looks. And that's how the correlation looks. Now, on the face of it, this is pretty amazing because here you have a well-defined bunch of points up here, well-defined down here. You'd say if you're going to put a correlation between them, it would go like this. Yeah, there are some points in these quadrants, but not very many. So how can we have a negative relationship between the two fields? Well, the fact is, it's not a negative relationship between the two fields. It's a negative relationship because the pulsar astronomers don't use the IAU definition of field direction. And I like to emphasize that because it's not well appreciated. The fact is that anti-correlation is really a correlation. And when we define magnetic field according to the IAU definition, a positive field points away from us, just like the universe is expanding with positive velocities. And if you write the equation, then the rotation measure is negative NEBL. Everybody always forgets this minus sign because the pulsar astronomers don't use it, and they're the ones who write this equation most often. Now we can do a little more with this correlation. That is, we can make an estimate for the magnetic field strength in the WIM. And I spent a lot of time last night doing this because of a conversation I had with Glenny's yesterday. So let me walk you through it. The data here, delta RM over delta B, is this line, crudely, very crudely. And that's about equal to 6 radians per square meter. And I multiply that over here by the number of neutral gas atoms divided by the number of neutral gas atoms. That's equal to 1, of course, but I want to carry that ratio down so I can, in a later equation, get the ratio of neutrals to ions. Now, by definition, delta RM over delta B is equal to the number of ions, number of electrons, times 0.8 radians per meter squared per microgauss. So you can put these two equations together, and you can find the ratio of the magnetic field in the WIM to the magnetic field in the NIM, and that's equal to 6 over 0.8. That's these numbers here, 6 over 0.8, times the number of neutrals divided by the column, that's the column density of neutrals, divided by the column density of ionized. That's a number we know because when we look towards the galactic pole, that's a well-defined ratio, and it typifies the ratio of column densities of ionized and neutral particles. And that's equal to about 1.5. And then we have to divide that by the number density, by the column density of neutral atoms in units of centimeters and minus cube parsecs. For most of our data, that number is equal to about 100. And when you put all this together, the ratio of field strength in the WIM to the ratio of field strength in the neutral medium is typically about 0.1. That means the field is weaker in ionized regions, and the field basically has no dynamical effect. It's a very high beta plasma. Let's see. If we go back to this correlation here, I want to talk a little bit about these guys in these two quadrants. They are the so-called nonconformists. A lot of us pride ourselves in being nonconformist. I try to be as nonconformist as possible. That's why I work in the business of measuring Zeeman splitting. So let's look at a map of these points, and in particular, I want to look at them associated with the North Polar Spur. Now, first of all, let's look at the Faraday rotations. And rather than looking at all of the, rather than trying to worry about the strength, let's just worry about the sign, S-I-G-N. So negative rotation measures are like this cyan, and positive rotation measures are like in red, and that's the whole sky here, and that's, of course, the north. And the North Polar Spur in this projection comes around like this. The center of that big supershell is kind of in the middle down here. So we can only see stuff that's on the upper edge and the left. And here's a map of the Zeeman detections at these high latitudes. This is the southern sky, so there's nothing down there. And the red are the nonconformists, and the black are the conformists. And you can see that these nonconformists tend to cluster. This is the Orion region down here. They cluster in there, but I'm not going to have time to talk about those. So let's look at why these might be different. Why are they nonconformist? Well, to do that, I want to compare them with the velocities of the gas associated with those detections. So here's the same map that I showed before on a slightly different scale. So I can blink it with the velocity of the gas. After all, when we measure Zeeman splitting, we measure a particular component of velocity of the neutral 21 centimeter line. So here's the LSR velocity of the points for which we measured Zeeman splitting, and the nonconformist points here are up here. I'll just blink a little back and forth. So there's the nonconformists, there are the velocities. And you can see that the nonconformist points all are down here having red and orange. They're down here with negative velocities. Whereas all the conforming points are up here with, in this part of with 0 and positive velocities. So this shows that the nonconforming points are made that way by velocity differences in the ISM that are associated with the points we're measuring. And that is an indication that the field is being perturbed by the velocity. The magnetic field is being perturbed by the velocity field. And we can understand that velocity field a little by looking at the following diagram. Suppose we have an expanding supershell here, expanding with velocity v, and we're looking at it from over here. We see the Doppler correction, and the Doppler correction is simply the line of sight velocity. It's the component of velocity along the line of sight. So out here at the edge of the shell, all the velocity is across the line of sight, so we see 0 velocity shift out here. At the polar cap, we see stuff coming towards us, and on this side, of course, it's going away from us. And so if you look at the locus of a constant Doppler shift. It's a circle in the sky like that. Now let's see what the actual gas looks like when we look at channel maps of the North Polar Spur. This is channel maps of the 21 centimeter line. There are all the points we have. And I'll run through these fairly fast. So you can see that structure growing bigger, now growing smaller. And that's a pretty good representation of an expanding shell. And the point I want to make here is that these points, the red ones are the nonconformists. Are the ones we see in filaments like that are radially expanding and have changed the field strength, the field direction that we detect when we do Zeeman splitting. Okay, that's, I can't figure out how much time do I have?
Probably you can speak another minute.
Well, okay. I did want to also mention that this is not the only big supershell in the sky that we see. The superbubble we know about which we know most is the Iran Eridanus one, and here's a picture of that. Red is the H alpha line, green is the 21 centimeter line, blue is the X-ray. There's a hot X-ray gas that's overlain by the cooler neutral and ionized gas that has been swept up into a shell like this, and that shell is expanding at about 20 kilometers per second. And I don't have too many measurements of that, but when I do the modeling of that shell, I just wanted to point out, find typically the line of sight component of magnetic fields about 10 microgauss, that's from Zeeman splitting. And then you look at the emission measures and stuff like that, you find typical electron densities of 6, thermal pressures of the WIM of roughly 10 to the 5th centimeter to minus 3 Kelvin. That seems like a lot, but remember it's an expanding shell. That's comparable to the dynamic pressure. The total magnetic field, of course, is twice that, which is about 20. The magnetic field pressure is comparable to the WIM pressure. And that's the other large supernova that's near to us. Okay, that's it. Oh, I should say, we have plans to do more of this kind of work using this telescope in Canada. Tim Robichaud is up there as a permanent employee, and he's working on getting this telescope ready to use for more such measurements.
So Carl, it seems like you could, since you have this sort of like onion shell structure with these super bubbles where you have the neutral gas and the ionized gas separated, and you can measure the field strength in both, it seems like potentially you could do something similar in the diffuse ISM that Dick Crutcher was doing in the cores, where he was taking measurements of Zeeman in the envelopes and in the central regions of the cores, and then comparing that with how the magnetic field might be diffusing in those regions. Is that something that you've looked into doing or thought about at all?
I haven't thought about doing Zeeman measurements in emission since the telescope fell down.
Maybe Tim will do it. I don't know.
Maybe Tim will do it.
This telescope seems
I
to
certainly
be
won't.
in better shape.
By the time he gets that telescope ready, I'll be long gone.
It's not possible to do that in absorption, based on what you were showing.
Well, it's hard to find positions. In absorption, you're restricted to where there's a continuum source. and there just aren't enough strong continuum sources to be able to do a reasonable job at mapping. It's best to do what you can, of course.
Carl, what's your current thinking on the sheets versus the cylinders for the filaments? Just because, I mean, what you're showing with the shells, right, that it makes sense that they're then sheets, but they're also filaments. And so I'm just wondering what your thoughts are on that as things have evolved.
Well, I used to think that all these things were filaments, but I think there's a lot of sheets we see edge on, but also filaments.
Right, that it's a mixture.
Yeah, it's a mixture. And one could kind of study that by looking at these filaments or these sheets or whatever they are, these column density enhancements, and look at the velocity where they're strongest, and then look away from that velocity and see if that structure goes away suddenly as a filament would, or whether it evolves a little bit with velocity as you move away from the center.
And Josh have been doing that.
Mm-hmm. Yeah, there's a lot of work that there could be done there, and I think it would be very interesting to do because it should be unambiguous what the result is.
Okay, let's think. Now the discussion
Okay, I am a long way from home intellectually. This is my first time, I think, ever attending a magnetic field or interstellar medium oriented workshop. And I'm also, huh?
feels good, doesn't it?
Yeah, sometimes. I'm also woefully unprepared. I wrote a paper relevant to the subject a few years ago, and I got interested in it, and then I got distracted by my regular job, which is something else. And just a few days ago, I decided to take a train up for the day to maybe reacquaint myself because I'm looking for new things to do. And then Blakesley asked me to lead the discussion. So, like a conductor, you don't have to bring an instrument, so I am going to be discussion leader without actually bringing anything relevant in terms of information or scientific results. I do like this picture. It looks like Van Gogh had anticipated all of this magnetic field structure, including star-forming regions, more than 100 years ago. I don't have much to say, but I do want to show you just a few slides. So the reason I got interested in this is that I'm an early universe cosmologist primarily, and there is this signal in the cosmic microwave background polarization, this B mode pattern, that we've been looking for because it may arise if inflation produced a stochastic gravitational wave background. A polarization map can be decomposed mathematically into E modes and B modes. It's a completely and utterly unambiguous mathematical decomposition of any polarization map. Of course, though, when we look at the sky and try to look at this primordial signal, there is polarized emission at cosmic microwave background-like frequencies, several hundred gigahertz. There is emission from the galaxy, from dust and synchrotron. And what we're hoping to do in the cosmic microwave background game is separate the cosmic signal from the galactic signal through observations of a number of frequencies, noting that the cosmic microwave background has a perfectly black body spectrum, whereas synchrotron has a steeply falling spectrum and thermal dust emission has a rising spectrum. So if we can measure the polarization pattern of a variety of frequencies, in principle, we can decompose it into these different components. This is good. This is how things have worked so far with the cosmic microwave background. But the signal that we're looking for is very, very feeble. And the measurements have to become increasingly precise, and the modeling has to become increasingly precise. And one of the limitations that we're beginning to face is that the dust frequency spectra are uncertain. The cosmic microwave background is a black body. That's a very black body. This thermal dust is nominally a thermal spectrum, but it's not derived from first principles. It's a phenomenological fit, theory-motivated phenomenological fit that's worked quite well for most work so far. But we now know from Planck that it's not precise, and there are variations from place to place on the sky. And so we have to start thinking about whether there might be other ways to verify the results that we obtain using this type of multi-component separation, or benchmarking it, or improving it further. So I was very, very, very thrilled when I saw this paper by Susan Clark and Josh Peak and collaborators a few years ago, where they pointed out that with these H-alpha maps, which look like, to me, like that, that you could essentially reproduce largely the structure you see in the Planck polarization map. So this is the magnetic field inferred from the Planck 353 gigahertz polarized map. And I was amazed to see how much of the structure is reproduced by those H1 maps. And we saw more of that today. And I'm really eager to see how well that can be pushed. How far can we actually go with that? So since I'm leading the discussion, I'm not going to say anything else, but I brought a few questions to hopefully spur other people to speak up, because I don't have anything else to say. So question number one. One thing I'm curious about is how well can a that's supposed to be ISM. So, how well can the types of ISM dust magnetic field maps that we've obtained from H-alpha, from infrared observations, etc., help mitigate the Cmv polarization foregrounds? So my primary interest was primordial B mode searches, but it's also important to know that CMB S4 and Simon's Observatory are going to be measuring polarization also on very small scales in an effort to learn about dark energy, neutrino masses, gravitational lensing, etc. And so it will be important to understand how these types of ISM magnetic field maps can help with the foreground subtraction for those smaller angular scale measurements that are required to do those things as well. The second question I have is, of course, these measurements are interesting even for people who aren't cosmologists. There's a lot we can learn about the interstellar magnetic field, the interstellar medium, the interaction of dust and gas, neutral gas, molecular gas, etc. And then there are also connections with MHD turbulence theory, because that fluid is magnetized. And one question I've had in learning about this is, what is really the connection between what is done in terms of MHD turbulence theory? People write papers with equations or simulating, idealized MHD situations. What's the real connection between the two? The other question I have is, what are the big questions? This is a question as an outsider. You may have answers yourselves. I'm curious to know, what is the big question that we hope to, what's the answer that we hope to get by studying the distribution of magnetic fields in the Milky Way, the dust distribution in the Milky Way, the gas distribution. Are we learning about the galaxy? Are we learning about the formation of the galaxy, the disk, the spiral structure, star formation? And the other thing, this question came up in Brandon's talk, which I thought was interesting. He was talking about quantitative models. And I know that there's lots of work that has been done on quantitative models, but there's also physical models that's different. And I was surprised to see the term quantitative model show up in Brandon's talk, because I know that he's done physical models as well. So I wanted to say one more thing. There was a paper that appeared just a few days ago that is relevant, that I don't think we heard about. So this is a paper by Kim, Choi, and Flauger. And what they did is they actually simulated, as well as they can, the region of the local galaxy that is responsible for most of the foreground polarization that we see in Planck. And they tried to put everything that they could in there. It wasn't an idealized MHD turbulence simulation. And so to me, this is, a very good faith effort to try to understand what it is that those polarized maps are telling us about the real local universe. And one of the things that I thought was very interesting is that this sentence over here, we find large fluctuations in the EB asymmetry and TE correlation depending on the observer's position, and temporal fluctuations of interstellar medium properties due to bursts of star formation. Which is interesting because it suggests that these mysteries that we've been trying to study, E to B ratios that we see in the Planck maps, the TE cross correlation, might not necessarily reflect anything fundamental about, MHD turbulence or the ISM at large, but some random local conditions. Yeah.
I and David could comment on whether, looking at your idealized models, do Kim et al. Likely have enough resolution to be able to say something useful? Because it seemed like you were suffering already at 512 cubed, and I don't think these are even that resolution effectively.
I wouldn't be so brash as to say it's not useful. Alexi?
I think Shengu can explain better what kind of resolution.
Yeah. I'm sorry. I should also ask you to comment in light of the previous talks.
Yeah.
I am very positive actually on their results.
So there are several things, especially concerning about the numerical resolutions. Especially for the number of zones, we have about 256 across the horizontal direction, and many zones across the vertical direction. And also we have a higher resolution that we can also test. But the thing here we see was with this resolution, we have a much steeper slope in the EEMBB power spectra, mostly due to the radial projection effect. So that we actually did another experiment just to the flat sky projection as Alexei did, and then Lapide analyzed that, and then he got the nice inertial range that reproduced this Alexei's slope nicely. And then so that we also have some resolution comparison between the 4 parsec and the 8 parsec model, so that we have also a similar result in the EB ratio and TE correlation, but the slope was steeper in the 8 parsec model. So the thing is, the mode is mixed between this inertial range and the dissipation range when you do this radial projection, so that make it everything some steeper. But the EB ratio and the EB power asymmetry and the TE correlation was less sensitive to this effect. So that's why we are more focusing on these numbers. So yeah.
Planck paper, there's a range of E to B mode as a function of, both frequency and also position on the sky. I think that's actually consistent with the fact that in simulations like Chang'e simulations and what we know from observations of the ISM, we don't have just like one sonic Mach number and one alpha Mach number and one plasma beta. There's actually a diversity of these parameters, which would then, I think, very nicely explain why you see these large fluctuations in the context of the MHD turbulence picture. So I think all these things are starting to come together, actually.
Yep.
I agree with that, and I think this is actually great motivation for having both what you called physical models and what I guess we're now calling quantitative models, right? We want to understand physically what is causing these different parameters in the dust polarization. Even if some of it is set by our particular location in the galaxy, that's still a physical quantity that we would like to understand. And then when we come to a day where we have our map that we want to actually take the polarized foreground signal out of, we're going to want to know our best guess of what the actual sky that we ourselves are looking through is. So we need both. Right?
Glenn?
That one. So I had married someone at one point and believe that what he told me was that the dust that's making this emission is quite close.
Yeah.
We look at that, for instance, when you look at RMs, you're penetrating the entire galaxy. But we're seeing a very nearby part of the magnetic field, I believe. And I just wanted to have someone disabuse me of that if it's not right.
I think that's correct.
Yes, it's.
Yeah. That is a part of the reason why we see the difference in due to the different observers' position, even for the same snapshot.
Alex?
Could I ask you to show this list of questions? And I would like to comment. I would like to comment on this interstellar observations and MHD turbulence theory. So far, I think there is a very good correspondence between what we know, beyond what this EB ratio is giving us, and the compressible MHD turbulence theory. And I have no actually idea how you can avoid having turbulence in the high Reynolds number media steered in the interstellar media. So the correspondence between this requires both analytical studies, and we were doing this, and observational studies. What we should remember when we're doing that indeed we're dealing with multi-phase media, which can give us additional complications. We also have the problems with the direction from which we are looking at the volume of the interstellar media, because it can, and we showed this analytically, result in different spectral slopes. So we have a volume filled with uniform MHD turbulence, and you think, okay, we should have Kolmogorov spectrum. No, it depends on some geometrical factors, and it can be not Kolmogorov, it can be some universal -3 spectrum. So it's interesting in terms of this E and B ratio that MHD turbulence theory with the pretty reasonable alpha and Mach numbers can explain this E and B ratio and other parameters without any problem. However, yes, there are some structures that should be introduced and studied. And Axel mentioned that there is also this helicity, which also can do this. But I think still this is a very productive way of studying the processes in the interstellar media.
Is the ISM the highest Reynolds number fluid that we deal with in plasma?
Well, the Reynolds numbers can be starting from 10 to the minus, 10 to the 5, 10 to the 10, and larger. So we usually in experiments, you get turbulence if you have a Reynolds number a few, or in the pipes it can go up to 100, but we definitely have such a Reynolds number in the interstellar media, so it is turbulent.
Yep.
Just a brief comment. I think in going forward from this to further doing science, I think it is very important to combine different approaches and keep this field as diverse as possible. I mean, You can include a lot of astrophysics and physics and do what Chang'e does, basically. This is beautiful simulations, right? But you also need a complementary approach of very idealized physics in simulations and theory to connect to the physics of turbulence, which is non-trivial, guys, right? We know that. So MHD turbulence.
The only thing I understand. The only thing I understand about MHD turbulence is that it is non-trivial.
Yeah, exactly.
That's probably enough.
Yeah. So we don't know much actually, and in order to interpret observations, we really need all complementary approaches.
Actually,
and larger community basically working on this.
Actually, I have a related slide. So I had one more slide. Well, I had two more slides. I was also wondering whether the SH seen in the cosmic microwave background also shows up in interstellar medium. You all know about this SH that showed up in the cosmic microwave background.
Where's the IT?
So I was trying to think of a list of observables that are being brought to bear on our efforts to map the distribution of dust and magnetic fields in the ISM. So I guess there was something about fast radio bursts that was discussed.
Nope.
That's none of this?
Didn't happen.
Huh?
He was sick.
And he was talking about extragalactic.
Extragalactic, it wasn't here. Okay. Okay.
There's pulsar RMs also.
Oh, yeah.
Extragalactic. And of course.
Each one.
There we go. Sorry. Oh, this is the wrong guy. That was bad. That's the wrong guy. There it is. How'd that happen? So, pulsar dispersion.
Well, you could drop it into Faraday Rotations, but often one's thinking of
Also dispersion measures.
distant objects.
In this case, I also would advocate both velocity gradients, the synchrotron intensity, and synchrotron polarization gradients.
Velocity gradients. What else? Synchrotron?
Synchrotron intensity gradients and synchrotron polarization gradients. I can show you how they work.
And of course, H1, 21 centimeter.
Oh, yeah. Sorry. Thank you.
If you want to understand synchrotron emission, you have to know what the chemistry and electrons
Yes.
are doing. Lots and lots of AMS.
Yeah.
Data on
Yeah, that's an embarrassing omission. Anything else?
Faraday tomography is, of course, maybe implied by that, but really in that sense was not mentioned.
Oh, yeah, Zeeman didn't get up there.
Can you use your seat mic, please?
Yeah. Probably, yeah.
So I have a potentially we can have also the atomic and ionic alignment not of dust, but ground state alignment of and Boulder-Coulafis effect.
What's that one?
Ground state alignment, atomic ground state alignment.
Okay.
And also Boulder-Coulafis effect. Dick can say more about that.
Linear polarization and spectral lines.
Oh, yeah. Okay.
But these are different still entities. Atomic alignment and this Boulder-Coulafis effect.
Yeah. What about
different effects.
What about this? My guess is this is not relevant, but I thought I'd mention it. So, is there any
diffuse interstellar
possible?
bands? Is that what that says?
Huh?
That's diffuse interstellar
Yeah,
bands? Is that what it
diffuse
says?
interstellar bands. My impression is probably too large distance scales.
They're relevant for mapping the dust distribution in 3 dimensions, which is very helpful for modeling the polarized dust signature.
And the distance scales are appropriate?
Sorry?
The distance scales are appropriate?
Yeah, some of these DIBs track very linearly with AV, which is why you can use them to constrain the total.
So the useful thing is if simulators produce maps of all of those things so that we can compare them.
Well, the simulations exist. It should be straightforward to put the observables in, I'm guessing. Yep.
Rather careful about what the simulations can actually do. For example, just as an example, if you want to do an H-alpha map, you need to know what your ionization is doing, which is photoionization. And we have no simulation that has feedback and magnetic fields and photoionization all in the same simulation. These remain extremely difficult, non-trivial simulations to do to even get a first decent approximation to all the observables.
Good point. Actually, I have something relevant.
I would also add that in addition to the approaches of having many observables and different simulations, what Eric showed in his talk of this Turbustat statistical database can be extremely powerful because not only can you distinguish the statistics of turbulence in your data or in your observation, but you could also potentially tell if 2 maps are similar or different based on their statistical properties. So I think in addition to the simulations and observations, we should also think of statistical comparisons between all of these.
Yes.
I know, Blake, you're responsible, therefore. You should say whether we should stop this discussion or.
If people are thirsty.
But I know that some people are leaving.
Yeah, so I think we should wrap up soon. We have drinks and snacks waiting for us outside. We get first dibs, so at 4:30 there's going to be a Flatiron wide cocktail event. So everyone is welcome to hang out and mingle and drink as long as they would like. So at 4:30 we're going to have several other people joining us, but for
Okay,
this,
in this case,
it's just us.
should we thank Mark?
Yes.
And I would like to thank Blakesley for organizing this wonderful event.